Welcome back. This is the final section of Chapter 9, Nuclear Radiation, and we're going to be talking about some more industrialized processes, nuclear fission, and then also a little bit about nuclear fusion. Nuclear fission, what you do is you bombard a nucleus with a small particle, and the particle is moving with enough velocity that it goes through it and splits it apart. Okay, and so you're left with two pieces where you once had one, and by doing that you extend a lot of energy. Okay, so this is a very high energy process. Nuclear fission, for example, most plants you will see them talk about is U-235. An unstable nucleus of U-236 undergoes fission, that is, it splits, because you're taking a neutron and you're bombarding U-235, so that turns it into what? A very unstable U-236. Because it's moving with such velocity, okay, it continues through and it splits it apart basically, and it splits it into two pieces. One has a mass of 91 and atomic number 36, and the other piece is 142 and 56, and then you're left with 3 neutrons when you get, and that's really important, and that's why it can produce so much energy. Okay, because once you start this, okay, and so you go through, you split this one in two, then you have 3. You started with 1. Okay, then you made 3, then you take that one and it splits and you make 3 more. This piece split, 3 more. Each one of these that splits goes on to split again. This is called a chain reaction. Okay, so each one of these U-235 atoms produces 3 neutrons, and those 3 neutrons can then go and split other, and so this chain reaction just continues on. You have to be able to stop this at some point, or it will not stop. So in nuclear fission, the total mass of the products is slightly less than the mass of the materials. Now, you can't violate the law of thermodynamics, but that missing mass isn't lost forever. It is just converted into another form called energy, and it does follow Albert Einstein's E equals mc squared, where E is the energy, m is the mass lost, and c is the speed of light, 3 times 10 to the 8th meters per second, which is what the speed is of those particles. And so if you undergo fission of 1 gram of U-235, you can produce the same amount of energy as 3 tons of coal. So you got a gram of U-235 and a ton of coal, right? So that's why it's very, very, very efficient. All right, if we want to complete the equations for these, they're still just as easy as we had before. It's adding, okay? You have 1 neutron is going to bombard U-235, right? So 1 plus 235 is 236. 0 plus 92 is 92. So whatever's on the other side also has to balance. We know we're going to get energy. We're going to get 2 neutrons from this particular bombardment, from this reaction and fission. We know one of the pieces is tellurium. That's tellurium-137, which is atomic number 52. Okay, so same thing. We got 137 plus question mark plus what? 2, because we got 2 of those, equals 236. So 236 minus 137 minus 2 equals what? I think it's 97. let's see. Yeah, 97. And then 52 plus something plus 0 equals 92. And that is going to equal what? 40. Okay, so we're going to get 97 over 40, and that's going to be zirconium. All right. So this ended up being 236 minus 139. Okay? Because you had minus 2 minus 137. Alright, so that's the answer. So hopefully you got that one right. Remember, these balancing these are really, really easy. All you have to do is make sure that the numbers add up on both sides. This one was the first little tricky thing here because you had 2 of these, so you had to remember that that was 2 times 1 was 2. So I just want to mention briefly nuclear power plants because, you know, they probably are going to be a big part of our future. In a nuclear power plant, you use fission. Okay, that's all we've been talking about is fission to produce energy. You have control rods here that absorb neutrons, and what they do is they slow that reaction down, so they control how quickly this cascade, this chain reaction occurs. And so they actually then heat up water, and that water generates steam, just like at a coal-powered steam plant, that will then generate electricity. The steam is then cooled, put through chillers, and then brought back and ready. So these control rods are what keeps this reaction under control. That's why the control rods have to maintain, and they have to change them out on a regular basis. These things right here are what they have to dispose of. And when they do, they are very radioactive. So that's the waste that they're having to get rid of. Now, all of that we've been talking about was fission. And when we were doing fission, we were busting things apart. Nuclear fusion is where you combine things, okay? It has to be super duper high temperature, okay? And one place where it happens is in the sun. Yay! Okay? So nuclear fusion happens in the sun and in stars, and it releases large amounts of energy that there's no way we could control. And so basically what happens is you have heavy hydrogen, they call it, hydrogen with 2 neutrons and a proton, okay, and then hydrogen with 1 proton and 1 neutron, and they combine together at these super duper high temperatures to form helium and a neutron and energy. And so the hydrogen atoms combine in the fusion reactor at very high temperatures, okay? We don't do this. All right, so that's all we're going to talk about fusion, okay? It happens in the sun and all that. Okay, so let's decide on these if it would describe nuclear fission, nuclear fusion, or both. Okay, the nucleus splits. Fusion or fission? Fusion or fission? Fission, right? Large amounts of energy are released. Both. Small nuclei form large nuclei. Fusion, yeah, they combine together. Hydrogen nuclei react. Fusion, right? Because you have hydrogen and hydrogen. Okay, and several neutrons are released. That would be our buddy, what? Fission, the one we use. Okay, so you need to know the differences between those. Mostly what we talked about were fission, they sound way too much alike. Fission reactions, okay? Fusion only in the sun where you combine things together. That's something we really can't control here on Earth. And that is the end of section 9.6, and that is the end of chapter 9. I hope you've enjoyed it. I think radioactivity and nuclear reactions are pretty cool.